I have two really nice examples here for you if you're interested in trying to figure out work. Now, typically work examples are rather simple. Now, these ones will make you think a little bit, okay, and it may surprise you. So here's the first one, and then here's the second one. Okay, so one is actually dealing with friction, which is the second one right there. All right, so let's tackle these two examples and let's try to solve them and give you some sense of how to approach these style of questions. So an object experiences a constant net force of 25 newtons. All right, so we have 25 newtons to the right. Okay, so that is the net force. Initially, the object is moving at a speed of 1.5 meters per second. All right, so we know that we are moving at a certain speed, and then if we have a net force, that means we're going to be accelerating. So if the force is present for 2.5 seconds and the object has a mass of 25 kilograms, so this is 2.5 seconds and then 25 kilograms, then what amount of work has been done on the object? All right, so it's a nice question. So now let's recall in terms of the given pieces of information, and we can try to map this out for ourselves. Okay, so let's imagine, so here's the object. I'm going to do a free body diagram. So it looks like we have, okay, so this is the net force. So I'm going to say this is F net, and that is equal to 25 newtons. Okay, it's to the right. Now the object is moving, so it is moving in this direction. Okay, and it has an initial speed, which is 1.8 meters per second. Now, we also know the mass of this particular object, so this is going to be 25 kilograms, so that's useful to know. And we know that it has been moving, okay, with this net force so this is going to be the change in time. So the total time is 2.5 seconds. So not very long. So let's take a look and see how we would calculate this. Now, it looks like it's moving in exactly the same direction as you have your force. So that makes our life easier because that means work is just simply equals to force times the actual displacement, okay, that we have. So now these are in magnitude form. I'm going to drop the vectors here. And because they're in exactly the same direction, so we don't need the cos theta between them because that would have been just equal to 1. So this we have, okay, so the actual force we have, this we do not have. So this is something that we're going to have to try to find. Now you can find this in many various ways. Now we do know what the initial speed is. We know what the time is. All right, so within here, so if you think back, okay, so we have delta D is equal to, so this is one of the kinematic equations, so this is going to be VI times delta T plus 1/2 the acceleration, okay, so the average acceleration that we have times delta T squared, so that's one of the kinematic equations. Now I have this, so I have that, I just don't have this, which is the acceleration of this particular object. So how would I find that? So you're going to have to do this kind of from Newton's law, so Newton's second law. So F net is equal to mass times acceleration in this case. So this is going to be 25 kilograms. Now notice this is going to be 25 newtons. That's your net force. So you can certainly find what the average acceleration was. I'll just keep it at A. Now this one is very simple because it's 25 divided by 25, which means that A is equal to 1 meter per second squared. All right, so I'm just going to write it like that. So now that I have this, I can substitute it back into here, and that's going to give me the total distance, right? So in terms of the total distance, which is covered. All right, so if I bring this entire thing down, so I'm going to just say, okay, so delta D is equal to, so now this is going to be 1.8. Notice this was 2.5 seconds, plus this is going to be 1/2. This is going to be just 1, and this is going to be 2.5, and this is squared. So let's see how far this actual object has moved. I can take up my calculator, can substitute it all back in. So 1.8 times 2.5 plus, and I'll do this all, I'll put it actually all in brackets, a half, well, it's the same thing as 0.5, so times 1. So that's nothing really that we need to put in there, but 2.5 we do. Okay, we need to square that. So we have this, and so that's going to be, I'm not going to round here at all. I'm going to just keep it because it's an intermediate step. So I'm going to just assume. So this has moved for 7.625 meters. So now in terms of work, so if you want to be able to find out what work is, so if you're going to be doing this, I can bring this back down in here and I can just substitute it all back in. Well, my force that was present, so that's 25 newtons, and times my actual distance, which was 7.625 meters. So there you have it. Now I already have this on my calculator, so it's easy to compute. And that's going to be 190.625 Newton meters or joules. Now, if you want to round this, you can always just double check to all the given pieces of information. It looks like they all had 2 sig figs, so we can just round this to 190 joules. So that would have been the work. Notice it is positive, so the displacement is in exactly the same direction as your force. All right, so that's question number 1. So that's a pretty decent one. Here's another example. So here's this one. Hopefully we're not going to have to do too much more work, but we may. Maybe I'll switch colors here just to make it exciting. So we have an object which is 225 kilograms. So I'm going to highlight this, okay, for myself. So that's the mass. It's sliding. Okay, so again, I guess it has an initial speed. It has a constant force of 95 newtons to the left. All right, is applied. Now this is an applied force, so it doesn't look like it's the net force, until the object stops moving. Okay, so the coefficient of kinetic friction is 0.18. Okay, so this is going to be important for us. So let me just start writing all of these things down for ourselves. So again, we can draw the free body diagram, just label everything. Okay, so here's our object. Now we're going to need quite a bit of information in here. So we're moving in this direction. So this is where we are moving to the right. Now how I know that is because of the speed. So that's going to be my initial speed there. So that's 3.5 meters per second. Now I know my final speed is 0. Now how do I know that? Because it tells me that the force is applied until it is stopped moving. So now, what else do I have? I have my forces. So here's one of the forces. All right, so that's one of them. That's 95 newtons to the left. So that force is trying to stop this object from actually moving on. But the other force that is going to be stopping it from moving, so it's going to be this kinetic force. Now, I don't know exactly how big this will be, right? So this is going to be the force of the kinetic friction. And that is always equal to the coefficient of kinetic friction times the force of the normal that we have. So now recall, so this is going to be, so you have your force of gravity, that's right there, and then you have your force of, normal. I'm going to be running out of space there, but, so since it looks like on a horizontal plane, there's nothing in terms of angles in here, so these two are going to be identical. So Fn is equal to the force of gravity, which we can certainly find out. So that's going to be mass, which is 225 kilograms, multiplied by the gravity itself, or the acceleration due to gravity. I'll just assume it's 9.8 meters per second squared. So now I will know exactly what that is. So I can put that in here. So 225 multiplied by 9.8. Okay, so there we have it. And maybe I'll just change the color so it pops out at me. 2205 newtons. All right, so that's my force of normal. Now I'm going to need that, in here. So for my force from the kinetic friction, my coefficient of friction isn't very big, but I mean it's big enough. So I'm going to have to multiply these together to get it. So answer times 0.18. So that's going to be 396.9 newtons. So that's definitely bigger than my actual, notice the applied force. So the actual kinetic force is slowing this thing down much more so, almost 4 times as much as your applied force. All right, so now, okay, so that's basically, so from here, this is my free body diagram, and now I can try to figure out what I'm going to need. Now I need to figure out work. So, you know, thinking back in here, so please remember, so this is going to be work is equal to, so now this is going to be force, right? So whatever total force that I have, so this is going to be the net force that I have, multiplied by the displacement. And now I have to be careful here, because notice that the force, my net force, is not going to be in the same direction. So in fact, my net force that I have in here, so if I was going to do this, it is equal to, if to the right is positive, I'm going to have negative 95 and minus 396.9. So this is going to be a negative number in here, okay, because it's in the opposite direction, okay, that I have. Now, if you're thinking about the definition, so please don't forget, so this is cos theta. Now, this cos theta that I have in here, the theta, because you're moving to the right, the force is to the left. Now, these two right here that we have, so this force, we need the magnitude, right? So this is the magnitude. Now, in here, if I did this, okay, so let me take this out. So I have this, and then 95, so they're in the same direction. So that's going to give me negative 491.9. Now, the magnitude of that is obviously positive 491.9. That's the magnitude, because it removes the actual sign if I'm talking about the magnitude. However, that negative is going to come back, because this is going to be cos of 180 degrees, which is just simply negative 1. So this negative 1 now multiplied by, so this is going to be your force, right? So the magnitude of the force times the actual displacement, which we actually don't have. So the displacement itself, now we have to be careful in here, so we can certainly find this out in the same fashion as I did for the previous example, so I can certainly do that. However, notice that they do not give me the amount of time. I can find out what the time is. But this again will bring me back to my kinetic equations, okay? So in here, so if I go back to my kinetic equations, actually the most useful one to use, okay, in order to find out that delta D is going to be this one. So that's V final squared is equal to V initial squared plus 2, the acceleration times delta T. All right, so, sorry, delta T. Delta D, that's what you're going to have as an equation. Now, I'm going to put up a link up above there to the kinematic equation, so to the motion equations that you have, and that's certainly one of them that you can use. It's not a common one, but it's a useful one in here. And the reason for that is because this is 0, that's my V final. My V initial, I know, is 3.5 meters per second. So that's going to get squared. Plus 2, my acceleration, okay, that I have, so this is going to be the acceleration itself. So that's this one right there. So I can try to find what that is. And then I'm going to have my delta D. Now, my acceleration is not very difficult to find. So this is going to be, I'm just going to do it aside here. So if we know what the actual net force is, so, you know, F net is equal to mass times acceleration. So this is going to be negative 491.9 is equal to, my mass was 225. So I can find out what the acceleration is by doing the division. So if I do that, so it's going to be that divided by 225. All right, so this is going to be 2.18, you know, 6 and a bunch of 2's, except it's negative because of that negative symbol. So that's what I would have over there. I'm going to keep this on here. So that's that acceleration in here. So I can put that in here. So it's going to be negative, you know, sorry, I'm running out of space there. So I'm going to have to kind of shift this over. I'm going to shift that. And that way I won't run out of space. So let me maybe clean this up a little bit. So negative 2.186. Okay, and I'm not rounding anything at the moment. All right, so what is this equal to? Well, we can bring this over to the other side. So that's going to be negative 3.5 squared equals, and then my delta D, so then dividing by this, so it's going to be division right there. So divided by 2, and then divided by negative 2, 1, 8, 6, 2, etc. So I can now figure out what that displacement was. So let me just clean all of this up. Now, this is going to be negative, so the two negatives will cancel, so that negative and not negative cancels. So this is now 3.5 squared divided by, and this is going to be divided by 2 times 2.186, and then a bunch of 2's. You can put a few of them in there, and that's going to give you, so this is approximately 2.8016, etc. That's the actual displacement covered. So this object is going to be sliding along, friction and the applied force are going to be in the opposite direction, so they're going to slow it down. So now with this, you basically have everything else that you needed. So you have this, right? You have the actual force, okay? So now you can figure out what the work is. So with this, okay, so if you substitute everything back in here, right, you can obtain what that will be. So let me do that. Okay, so that's work is equal to, so now I have the magnitude of the force, which is 491.9. The negative is dropped because I'm just talking about the magnitude. That's going to be multiplied by 2.80, 1, etc. times cos of 180. You can put in cos of 180 into your calculator. You should know that it's negative 1. And this will now give you the answer. So I have this multiplied by 491.9 and then multiplied by negative 1. So that's going to be negative 1,378 joules. And that would be your answer. Okay, so it would be negative because they are actually opposing each other. All right, so with respect to work, okay, so that's what you have. So the object is moving and then it basically dissipates, right? So if you're thinking about kind of energy, so it's going to be dissipating the energy, or the work is coming out of the object, right? And actually it's going to be transferred to, the friction, which is going to be heat, okay, that you have, and as you're applying in the opposite direction to you as well. Okay, so here, that would have been your second item. Now within here, I'm just going to peek. So it looks like the minimum was 2 significant figures. So this you can of course round now. And this would have been 1400 joules if you wanted to round to sig figs. But whatever your teachers ask you to round to is fine. This was a fantastic example. It's very challenging because of the fact that you have to figure out forces. You have to understand they're in the opposite direction to the displacement that is that you have, and displacement you had to find. So that was a really good one. Okay, and then just plug it into your work formula. All right, so that is it. 2 nice examples. Thanks for watching. See you in a future video. Bye, everybody.